Awesome. Okay. So the first thing from this that I want to do some review on is going to be sort of pertaining to reaction mechanisms. Like one, because they're a big part of these two chapters, but two, there's something that like we should be gaining a feel for as we're going, so that it shouldn't be the goal, like shouldn't be to just try to memorize what to do when, but to kind of have like this understanding of, oh, I get why this pair of electrons would attack this particular atom, that kind of makes sense. So I want to do some reaction mechanisms. I want to do them wrong and have you try to identify what it is that is sort of the incorrect moves that are being made there. Okay. So one of the ones we learned about this time around was, remember we have these different nuclei. I'm going to start with aldehydes and ketones, chapter 19 stuff. One of the things that we learned about was oxygen nucleophiles, and in particular water. Water is one of our only nucleophiles from this chapter that can react under acidic conditions, but we can also react it under basic conditions with the ketone using the hydroxide ion. Okay, so if I'm going to draw the mechanism of a hydroxide ion reacting with a ketone, so what is incorrect about this move here? But we got two views, so everybody take a second to look at it, I think, right? Make sure I got everybody. Yeah. Take a second to look at it and see if you can identify what's incorrect about this.
Just looking at it, I can see that because it's a nucleophile, so pretty much the hydroxide should be attacking the carbon-o-carbon.
Yeah, exactly. Yeah. My arrow is pointed just in the exact opposite direction, right? Should be the base of my arrow should be at the electrons that are, doing the attacking. The tip of my arrow should be at that electrophile. That's, the basis of all organic chemistry reactions is you have the electron-rich species, which we got that fancy name for the nucleophile, that's reacting with the electron-deficient species, the electrophile, right? So exactly, my arrow is exactly reversed. Okay, so I fixed that. I still got a problem here. And what is that?
That should drive the double bond up onto the oxygen there and create a negative there.
Awesome. Yep. So if I had just done this as one step, then I would be saying that my final sort of answer looks like this. And that should hopefully drive everybody nuts, because that carbon has 5 bonds, which is just not possible. Right. So the next step is, after that nucleophile attacks, that necessarily has to bump this pair of electrons up there. Okay. So then I'm going to get something like this, where here are my carbons. Here was my incoming thing. And then what's wrong with this structure as it's written?
You need a negative charge there on the oxygen.
Yeah. Right. So I haven't balanced my charges. I'm going to necessarily need to remember to put that negative charge there. If I was being really good, I would put in my dots like Wiley makes you do. But to truth be told, we get lazy and we. Yeah, I know. I was doing it myself, and I like made that mistake like 4 times in a row. It was like, oh my gosh, just do it. Remember the lone pairs. But yeah, and truth be told, we would really get lazy. And as long as you include the formal charge, then it's kind of implied how many electrons there are. Okay, and then from here, what do we think my next step would be in this case, right? So I guess where I'm trying to go with this is looking at this structure, something should look a little off or at least unfinished.
Something's gonna... Something's gonna...
leaving
so here, the problem is that I don't have a leaving group, right? Both of these, neither of these would be considered a good leaving group. I could maybe protonate it and make it water. That's a good leaving group. But before I would even get there, go for it, Andrew.
Oh, I was gonna say protonate the. I was gonna say that we could add water, but you just said that, so that's obviously not.
No. What I meant by that was, for one of these to be a leaving group, we would have to protonate it and make it water, because that would be a good leaving group. But you're absolutely right. We need we basically need to cap off this. right? That should be the one thing. So even kind of where I'm going with this is like the one unfortunate thing about reaction mechanisms, or the one thing that really trips people up, is when there's a base involved or an acid involved, because oftentimes it's just the solution that these things are floating around in that's playing that role. So exactly, we would have a basic solution, but we don't just have hydroxide ions. That solution would be in water. And so here you're sort of exactly right. We need to protonate that negative charge, and we would use water to do so. Right, so the last step should be to cap it off. Okay, and I actually kind of like the Wiley plus approach of just always using water or hydroxide or what do they call hydronium, the H3O plus. Another thing that you will often see though in textbooks would just be this HA, and this just means like generic source of acid, right? Or source of proton. Another thing that you would often see for the reverse would be generic base, or B, used, and that could do the job of a base or of deprotonating. But the Wiley plus homework always uses water. I kind of like that approach. Makes it a little bit less, a little more tangible, which I think helps. Do you guys remember what we call this? Anybody?
I can Google it.
Honestly, it's not. What's up?
Nothing. I'm being.
It's not. It wouldn't be the greatest sin for you to not remember, but this is what we would call a
Diol.
hydrate.
No, hydrate.
It could be a diol, but well, it certainly is a diol, but it's a very special diol because both of those oxygens are both of those alcohol groups are bound to the same carbon. So this is something special we call a hydrate. As we said in the lecture, the only compound that goes sort of in this direction to any significant degree is formaldehyde, when there are two hydrogens there. Most compounds do not prefer the hydrate direction. They go in the reverse direction. Okay. All right, so sticking with this reaction mechanism theme, it's kind of a long one, but it is an important one, so let's go for it. Do the reaction mechanism that you would get between these two under acidic conditions. And I'll tell you that the product that we're looking for is this guy here, and this guy also has a special name. This is an acetyl. And I'll say, you know, one of the things that should be your goal in this study session is to try to like, you know, quote unquote, cheat by using your notes as little as possible. Because, well, I mean, you guys probably have heard me say it, or hopefully have, that one of the biggest mistakes that I see students making, even good students, is just always studying with their notebooks open. And the problem with that is that you kind of like convince yourself that you know something that as soon as you close that notebook, you don't actually have a good understanding of, right? When we do a problem like this, I'm sure you guys know sort of exactly where to turn back to the lecture slides and back to your notes to get a hint of what's going on. But of course, you're not going to have that on the exam. So the goal should be to try to do as much from memory as you can. And then if you're like really stuck and you need to cheat, then of course you can go and look back. But first instinct, I know, is to like click to where you know this stuff is, but we just don't have, you know, you're not going to have that luxury on the exam. So doing as much from memory as possible is awesome.
So because this is under acidic conditions, we should be making these steps so that there's never a negative charge, right?
Boom. Yeah. So you
Okay.
kind of already, whatever, got the punchline that I was going for. One of the first things that I was going to do is say, this is the first step, right? And the problem with that is that then I would be left with something like this. And this negative charge right here, we really shouldn't have under acidic conditions, right? The whole negative charge things shouldn't exist is a little bit of a shorthand. It's really that strong bases shouldn't exist. And this is indeed a very strong base. And luckily we can make that shorthand because almost all of our strong bases have negative charges. But yeah, so then the first step here has to instead be what?
Wouldn't it have to attack like the hydrogen right there, the oxygen?
It would, which oxygen attacking which hydrogen?
Because I'm not sure if it'll be a water or if it'll be down right there. So that the oxygen can have a positive charge, so it can be in acidic conditions.
Yep. So, and this is again sort of one of these tricky things, is like you have this molecule and this molecule explicitly drawn, but you have to remember sort of that these are floating around in an acidic solution. So the first thing that we would do is use one of those acid molecules to protonate this oxygen, right? And the tricky thing again is that H3O plus wasn't explicitly in there. I just said acidic conditions. And that's how reaction mechanisms go, are things that are playing the role of acids and bases. You just got to know sort of by utility, or I know that I need to protonate this oxygen, where they're going to go. Okay. And again, another way that you would have seen this included would be, instead of using H3O plus, you could also just use like HA, generic acid. But again, I kind of like using the water. All right, my bad. I don't know what happened there. Hopefully I wasn't just talking to myself there for 10 minutes. Okay. So we're back here. You guys see me?
Yeah, I see.
Yeah.
Okay. Did you guys miss the whole spiel about the role of the acid? Or was
No, I heard
before
that.
I got cut off? Okay.
I heard
cool.
that. It got quiet for like 20 seconds and then.
Oh, okay, great.
Yeah.
All right, cool. Yeah, and again, just to hammer it home, right? The sort of hard part being that this guy wasn't explicitly included, but you know that you got to have that source of proton. You know that protonation step has to happen. So it's just kind of implied. All right, so from here, what can I do? Am I cut again? No, we're good.
I can hear you.
Okay, cool.
Could the double bond attack the base of the ring, and then the hydrogen from the diol attack where that negative charge would form?
So,
or the other way around?
Yeah, so the next step is going to be actually nucleophilic attack here. The one thing that I sort of, you had said something like the hydrogen doing the attacking. Hydrogen will like almost never play the role of a nucleophile unless we're talking about a hydride, like for example, our lithium aluminum hydride. I had said, and this is one of the things that you should have in your mind, is that hydride equals hydrogen nucleophile. But those are the only times that you're ever going to see hydrogen playing the role of a nucleophile is in those hydrides. So typically, instead, you're almost always talking about oxygens or nitrogens. We can talk about sulfur too. It's in the same sort of family as oxygen, but default will be an oxygen or a hydrogen nucleophile. And this particular oxygen is now a crap nucleophile because it's been protonated. So instead, we're going to use our diol oxygen. And as we said before, that means that this pair of electrons in our carbonyl bond has to be kicked up. And why is that? Because carbon can't have more than 4 bonds, exactly. Okay. All right. Now, what's going to be our next step? Again, one of the things is we want to keep in mind where we're going. Right? So something about this structure look kind of weird. And what is that?
This is just my guess, but wouldn't that own like alcohol attack the other oxygen that has a positive charge, or how would it?
In this case, it wouldn't, because you're saying something like this.
Yeah, something like
Okay.
that.
So first of all, instincts are pretty good in the sense that you have an electron-rich species attacking an electron-poor species. The problem is that here we sort of did this, even if we then kicked off this hydrogen or something, right? Because oxygen, of course, can't have more than 4 bonds as well. We would have okay, and that's sort of not going where we need it to be in terms of both of those oxygens being attached to that carbon.
All right.
Okay. It turns out that actually this positively charged oxygen is not a good electrophile, because oxygen's just really not a decent electrophile at all. You are right that this positive charge is the funky thing, but how do we get rid of that? What's going to be the easiest way to get rid of that?
Deprotonation.
Deprotonation. Yeah. So I'm going to take, and again, I'm going to use generic base just for fun here, but you could also use water to do the job in this particular situation. All right. So it's going to grab that, kick that pair of electrons back down. Okay, so this is what we call a Hemi Acetyl, meaning halfway there to our acetyl formation. And, you know, it's a neutral species. It's actually hard to get it to stop at this particular step, but nonetheless, this would be kind of you wouldn't be incorrect in thinking that this is a stopping point, because we got our neutral species, nothing's like got too many bonds or anything like that. But if I'm trying to get all the way to this acetyl here, I'm going to need to do some stuff. I'm going to need to get rid of some stuff here. So let me color these oxygens different colors. Okay. And looking at this structure up here, what are these 2 oxygens supposed to be matching down there? Like if I were going to color my acetyl, with the same coloring scheme of my Hemi Acetyl, which two colors would I use?
The blue and the purple. The green is going to be the one that gets kicked off.
Absolutely, right? So this guy is going to match that. This guy is going to match that. So that means I need to get rid of this somehow. Okay. And how do we get rid, let me get rid of my, well, that's fine. How do we get rid of that particular functional group?
We could have more, because it's acidic conditions, so the hydrogen could be donated to that HO, and then...
Boom. Absolutely. And really the thought process is, I need to get rid of this, but that's not right, which means it needs to be a leaving group. I need it to leave. But currently it is a crap leaving group. It's not going to leave in its current form. So what I'm going to do instead is turn it into a really good leaving group by protonating it. So now I have this bomb leaving group. And what is going to be that impetus that actually kicks it off?
The electrons will attack the positive charge and break that bond.
Yeah, totally. So I got this. Okay. But if I just did that, that would leave me with this here, with this carbocation. And carbocations don't like to form kind of like just for the heck of it, right? So even better would be if I had something kick this leaving group off, and that would be this pair of electrons coming and attacking here.
I was actually thinking the same thing right now too.
Cool, yeah. So that's I mean, it's kind of weird, and you're not like you're forgiven for thinking about carbocations in organic chemistry mechanisms. We absolutely use them quite a bit, but kind of if we can avoid them, they will be avoided. And so in this particular case, the attack on this carbon and the subsequent leaving group is actually, those two steps are going to happen concurrently. If you did it in two steps, it wouldn't be, you'd still get a heck of a lot of partial credit, but yeah. Okay, so now we're pretty close, but not all the way there. All right, so actually you guys draw me where we are.
You would have basically the acetyl in the top right corner, but the left oxygen would still have the hydrogen attached to it in a positive charge.
Yep. And then, so then our last step will have to be deprotonation of this guy. Okay, so I'm going to have this. Going to come along and attack that. Keep that there. That gets me here. Okay, now arrow-wise, I didn't do anything illegal, but what is wrong with this particular step?
It's acidic conditions, so no negative charges.
Boom. So instead, what's going to have to play the role of my base? It wouldn't be hydroxide.
H2O?
Yep, exactly. All right, so I can't have a strong base like hydroxide in my acidic conditions. So instead, my base will just be water. Awesome. And do you guys remember what the sort of fancy thing that we can use this cyclic acetyl for?
Acting.
All right, so this cyclic acetyl is a protecting group for aldehydes and ketones. Right, meaning that if there was, for example, an ester down here, we could then reduce, and that's the most common sort of use for these, protecting groups in this case. And that would only reduce the ester group. Oops, that's not how that goes. But leave alone this one, and then I can convert it back to a ketone. Well, I guess we could just, by using dilute acid. All right, so in this way, I've used this cyclic acetyl as a protecting group.
Wait, just one thing on the top one right there. You have an extra carbon though. Is
no, it's actually the bottom one that I'm missing my carbon. Oh. Right, because this carbon here is still going to be there after I do my reduction of my ester. So that carbon, that carbon, that carbon. All right, but that was like our special little use for that part of that cyclic acetyl in particular. Okay, and then let's see if we can remember if instead of using a diol, I used a dithiol. Do you guys remember this would be a thioacetyl? And this also kind of has a special role. Do you guys remember what that is? So I can convert cyclohexanone using this dithiol into my thioacetyl. And what special role does this thioacetyl play?
You can use the rainy nickel to
to chop it off.
Yeah.
Right. So if I'm looking at this molecule here and I want to chop off that ketone group, chop off that carbonyl oxygen, I can use this thioacetyl and that will reduce it. Thioacetyl plus rainy nickel, and that will reduce it to now there's just 2 hydrogens. Okay, so that was one of our methods that we learned for how we like literally reduce a ketone or aldehyde all the way to an alkane. And there was actually another way to do it. See if you can't remember that. Okay, so first we would use this guy here. I can't remember, I never remember what it's called. It's got a special name. Hydrazine. Okay, and what's our key functional group that we see with the hydrazine? Oh, Asia, what's up?
What's that?
What key functional group we got on our hydrazine here? What's jumping out to us?
The amine?
The amine, absolutely. Right, and there's 2 of them, which is why it's a little special in this particular case. But what do we know about, let's just take some generic amine and how they react with ketones or aldehydes. We got another special vocab word here. So actually, I'm going to use it just ammonia, the simplest one here. Well, no, I lied. So this will form what's called an imine, where my oxygen, like notice the similarity between these 2 functional groups here. Though really the difference being that nitrogen likes to have 3 bonds, so I'm also always going to have something sticking off on the other side. right? But this is the reaction between actually just a primary amine and a ketone, and that will form an imine. And so with hydrazine, it does the same thing. Only one of those nitrogen functional groups. Okay, but then what we learned is that we can use a base in water and heat, and that will cleave off that hydrazine group. So this is, we had these two methods for fully reducing a ketone or aldehyde. And this has to happen under acidic conditions. Okay, so if I have this primary amine, I'm going to form an imine. I'm using the heck out of cyclohexanone, so let's use a different one. What if I have a secondary amine? What do I get then?
Likes to have 3 bonds, so a single bonded nitrogen to the
Okay, yeah, so I got this, but what's actually, there's something else that's missing here. And that should be a double bond right here.
Dang it.
These we call ene amines. Right, you got the ene and then the amine. So let's sort of look at why these two form. And it has to do with the fact that they kind of share a particular reaction intermediate. I'm not going to do the full reaction mechanism because that would eat up a lot of time. But one of the last steps is, actually, I'm going to move some stuff around here. I lied. I'm going to get rid of this altogether. Okay, one of the last steps is when that oxygen gets kicked off. First of all, how do we turn oxygen into a good leaving group? We make it anybody? Bueller? That's not. How do we make oxygen a good leaving group? It's like almost always the same strategy, which is to turn it into water or to protonate it. Okay, so one of the last sequence of steps in this particular reaction, and again, the way that we're going to actually get rid of our leaving group is to kick it off at the same time as sort of nitrogen's doing the attacking. So that leads us with okay. And then the very last step in this particular reaction mechanism that gets us to my imine is just to have some base that comes along and takes that hydrogen. Okay. In our reaction mechanism for our secondary amine, we have a very similar sequence of events where I'm going to, oh, whoops, I'm not using that compound anymore. I've got my water or my oxygen that I've turned into a good leaving group by making it water. And again, you have your nitrogen pair of electrons coming down and attacking the carbon, and that's the impetus that kicks off that. So notice the similarity between this step here and this step here. Right? The difference with our secondary amine is I don't have a hydrogen to just deprotonate to make it a nice stable neutral compound. right? I've already kicked off my only hydrogen that I had. So in this case, it's actually what's called your beta carbon hydrogen that's going to be removed, oops, by your base. That sort of kicks off this sequence of events that leads to our enamine. All right. So despite the fact that I have very different looking products when I use a primary and a secondary amine, it all sort of stems from this sequence of steps, the like last two steps in your reaction mechanism, and how incredibly similar they are. But if you have a secondary amine, you can't just deprotonate it and make a neutral compound. So that's why it's actually the beta carbon that loses its hydrogen.
The side that ends up forming the double bond, that's what's that called? That's from the bond. Is it the more substituted one, or is there's another thing?
No, you're right. So in this particular case, the reason why I sort of glossed over that, but thank you. Yeah. So in this particular case, the reason that I chose that carbon to remove my hydrogen is now I've formed the more highly substituted alkene, which is going to be the more thermodynamically favored of the two. Right? Higher substitution always means more stable. In reality, you might have a little bit of a mixture of the two possibilities, but your dominant one will be that one that's more stable, that higher substituted one. Okay. All right, switching gears here. I'm going to draw a few benzene derivatives. Okay, which of these four could undergo nucleophilic aromatic substitution? Just to refresh your memory, there were like these three rules, three different criteria that a compound has to meet in order to be eligible for nucleophilic aromatic substitution. So of these four, A, B, C, D, which ones would qualify? Take a second and see if you can't spy that. Well, first of all, take a second and try to remember what those three rules are, preferably without having to look back in your notes. So A, B, C, D, which one can undergo nucleophilic aromatic substitution?
I'd say C.
C? Yeah, that is one. And actually there's another one too. Okay, so first of all, the first rule, very important rule, you have to have a strong electron withdrawing group in order to be eligible for nucleophilic aromatic substitution. Just to sort of recap, at the very beginning of chapter 18, we learned about electrophilic aromatic substitution, where the benzene ring was playing the role of an electrophile. And when that was the case, electron donating groups were good, right? Because they donate electrons to that ring, making it even more nucleophilic. Here, it's the exact opposite. We need it to have a strong electron withdrawing group because the nucleophile will attack our ring. The ring's actually playing the role of an electrophile in these reactions. Okay, so that rules out which one of these.
E.
Yeah, this guy can't, right? Because this amine group is a electron donating group. So that's going to make that ring a really crap electrophile. Okay. The second criteria was you have to have a leaving group. So actually all of these remaining ones qualify because I have that chlorine. So that one's good. The third rule, though, pertains to the position of that leaving group. Where does the leaving group have to be?
Ortho or para.
Orthopara, yep. So that's kind of my 3 rules for nucleophilic aromatic substitution. So that rules out B as well. So A and C are the ones that would qualify. Okay, and again, just sort of emphasizing reaction mechanisms. Take a second and draw me the nucleophilic aromatic substitution reaction that would occur between these two. All right, and again, key here, I got a good nucleophile, and now my ring is made electrophilic because of my electron withdrawing group. So take a second and see if you can't remember those reaction mechanisms. All right, go. Come on, buddy. You dance, Tony. Come on. Hey, Rudy. Hey, buddy. You done? Just kicking him out. I'm kicking him out. Where'd you guys go? Yeah. All right, so what's my first step? I'm going to have my nucleophile doing some attacking. Where on this ring is it going to attack?
The base of the chlorine.
Yeah, so right, this is going to be my leaving group. So that's going to be doing the attacking there. To be honest, you'd be completely forgiven for just sort of kicking that leaving group off immediately. The book actually first shows that it goes through this kind of a reaction intermediate. Oh, nope, line, that pair of electrons not there. And then in next step, this pair of electrons comes back down and kicks off the leaving group. So that gives me an H2. is what the book has, presumably because they're sort of showing that this pair of electrons, you can draw all those different resonance structures and show that it's stabilized by the electron withdrawing group. And that had a special name. It wasn't a sigma complex, but something else. I don't even remember.
It's Mesenheimer. I had it open for.
Nice. Okay. Yeah, and I think the big thing is that because of, the reason why it has to be orthopara is because one of the resonance structures, if it is in the orthopara position, will have that negative charge, that pair of electrons right there, where that nitro group is, right? So, okay. So that's why that orthopara, I guess that is the evidence, is that it has to be orthopara. I didn't think about that. Okay, well, I take back what I said then. You can't just pick off the leaving group in one step.
We cannot. We have to draw the. Okay.
Yeah, because now that I'm thinking about it, I was like, I don't understand how they would have evidence, but I do actually now, because you can't, when it's in the orthopara position, the base of electrons, one of those resonance structures will include having the pair of electrons at the base of the nitro group, and that wouldn't happen if the leaving group was in the meta position. So there is some so that's the evidence that this sort of structure right here, this intermediate, exists. Okay, and then if I wanted to actually create, just doing some practice of reagents, I wanted to create sort of dianiline. I don't think that's the name of it, but this compound here, how do I go about doing that?
Wouldn't you have to use zinc with mercury or something like that?
Yeah, it's zinc or mercury, and then acidic conditions and heat. So this is just one of ours, and actually, so what slide is that? Slide 68 is sort of a particularly important slide in this chapter, because it shows the functional groups that we can convert to other functional groups, right? We know how to add functional groups using electrophilic aromatic substitution reactions. We can replace our leaving group with the nucleophilic aromatic substitution reactions, but there are a few functional groups, nitro being one of them, that we can convert into another functional group. And so those can be particularly important, especially because they change that, change those molecules from being, or those functional groups from being orthopara directing to meta directing, or vice versa. In this case, we've changed our nitro group, which is a meta director, into the orthopara amine group. Okay, so let's just do a few examples where this is particularly consequential. I lied. This is, you have to follow it up with the base. Okay, so there's another one that we know how to convert, which is converting an alkene, or I'm sorry, not an alkene, an alkane to a carboxylic acid. How do we do that? All right, so this is one of the annoying things about organic chemistry, is to some extent there's just some flashcard memorization that has to go down with the combination of reagents. The key one here, and I'm pretty generous with partial credit as long as you get the key player in there. So in this particular one, my key oxidation player is that KMNO4. the full sort of list of reagents would be water, heat, and then you actually have to follow up with an acidic, they call an acidic workup. Okay, but I mean, if this was, I mean, obviously your goal is to know everything, but if we're sort of talking about order of importance here, if your answer on the exam was just KMNO4, that would still get you a good bit of partial credit because these other guys are playing sort of less obvious roles. This is our oxidizing agent that's doing the job.
If you said, hold on, Na2Cr2O, is that wrong?
No, that's another one.
Okay.
So that's these are two. This is actually, yeah. So that's awesome. This is the one that's on that particular lecture slide 68. But you're absolutely correct that in the last chapter or the previous chapter before this, we also learned that benzylic carbon can be oxidized with our other favorite go-to oxidizing agent, which is the sodium dichromate.
That's just what popped into my head, and I was like, oh,
so I mean, if you're thinking oxidation, that guy should be the first thing that sort of comes to mind. So that's good instincts. Okay, so then let's do, if we want to, so let's do two sort of similar multi-step synthesis problems. This one and this one. So how do I make these two? Everybody take a second and see if you can't give me the steps for synthesizing these from benzene.
Just one question. Oh yeah, I was gonna ask you about that right there. What you just erased right there.
The sodium dichromate?
Yeah.
Okay. What about it?
So for that, I mean, so if you have a carboxylic acid, that'll actually like bring it back to that's the original the methylbenzene.
No. You could use sodium so whenever you see, really the chromium is, because there are a few chromium oxidizers, that's the most popular. But whenever you see sodium dichromate, you think it's an oxidizer. So you could have used sodium dichromate in place of the KMNO4. The full list of reagents would be here, but these would accomplish the exact same thing by converting your toluene into carboxylic acid group.
Oh, okay.
And actually the crazy thing about those is it doesn't matter how long that alkyl chain is, it will still oxidize it, sort of chop off the remaining chain, oxidizing that benzylic carbon. Okay, and actually we haven't learned this explicitly, we will next chapter, but if I wanted to go the other direction from a carboxylic acid to toluene, right? Or, you know, sort of fully reduce it. What is one of the reagents that we've learned about that you think that we might be able to use? All right, again, that's not an oxidation reaction, but a reduction reaction. And we have one compound that we've learned about that's just like a super good reducing agent. Oh, it wouldn't reduce, never mind, I lied. It wouldn't go to toluene. It would go to phenol. Oh, it wouldn't be phenol, it would be. Anyways, we can use lithium aluminum hydride. So carboxylic acids, just like ketones and aldehydes, can be reduced to alcohols with lithium aluminum hydride. We'll actually learn about that next chapter, but this, so in the same way that I see chromium and I think oxidation, I see this and think reduction. Okay, so how am I going to get from here to here? What am I going to do first?
I did. I put the chlorine on there by doing Cl2 AlCl3, and then I added a CH3Cl AlCl3, and then I oxidized it with the Na2Cr2O7 H2SO4
Yeah,
H2O.
awesome. So actually, I had a little bit of a different scheme than that, but you're absolutely right. I should have used something like this. To emphasize just how the order of these steps matter. In this case, you could have put chlorine on first because that's an orthopara director. But if we do it like, say, for example, did it this way, the important thing would be that we have to put on the methyl group using that Friedel-Crafts. And then secondly, we would convert, or we would add on H2SO4. We add on that nitro group. And we would lastly do our reduction. No, I changed my phone. I had a chlorine group there originally, but it sort of messed up the point that I was trying to make, which is basically the order in which we add on that methyl group, but before we go ahead and oxidize it, we add on the functional group, as opposed to in this example, where I would add on my methyl group, and then I would have to oxidize it at the very bottom of the page. So my handwriting was going to look like absolute trash. Sorry. And then,
Very bottom.
What's up?
We actually can't see the very bottom.
Oh, bummer.
Yeah, there
You
you
see
go.
it now?
Yeah.
Okay. And then I can put on my chlorine, right? So again, the sort of point being is here, I need to direct to the orthopara position. So I'm going to use my methyl group to do so. Here, I need to direct to the meta position. So I'm going to oxidize before I then add that, because I can use my electron withdrawing carboxylic acid group to do that meta directing.
Quick question, couldn't we have also just had a carboxylic acid with a chlorine and use that as the Friedel-Crafts and skip the oxidation step?
You can't do a Friedel-Crafts with the, so that would require like this. This isn't something that would work. Basically, you can't do that in one step with the Friedel-Crafts. If that wasn't a carboxylic acid group and it was just a ketone, that would be fine. But this guy right here, we don't really.
Okay, if a ketone's fine, would an aldehyde also be okay?
Say that again?
Would an aldehyde also be okay?
You
if we
can
chop that.
If you chop that off completely?
Yeah.
Yeah, that's fine too. To be honest, I don't even know if this exists. This just looks kind of weird to me. It very well may, and I just don't know about it, but it's one of those things that I look at, my eyes go crossed a little bit. So we're going to err on the side of safety and just say that we can't use any sort of fancy. The only Friedel craft that we can use is the straight up, but why am I blanking? Acyl chloride. You know, no mixed functional group Friedel crafts.
And you said that was acyl. What again? I'm sorry.
This is an acyl, and actually we'll spend a lot of time talking about this next chapter, but this is called an acyl chloride, where you have, or an acyl halide if it was any other halogen, but where you have your halogen directly connected to your carbonyl carbon. These are actually super reactive and great for a lot of stuff. We'll learn about that next chapter.
Okay.
Yeah, those are acyl chlorides. Okay, so you guys are good. You put in your hour. Do you guys have any additional questions? Anything that you specifically would like me to go over? Damn. Anybody?
All of the answers for tomorrow.
All of the answers? Yeah.
We get one bingo, right? One freebie in the middle.
It would make my life easier, but unfortunately, no. You know, you guys are. I don't know if unlucky is the word, but of course, my main goal is really to torture you as much as possible, so that when it gets time for that final ACS exam, you guys just crush it. And unfortunately, last semester you guys did do really, really well. So I know that I can whatever, get some good grades out of you if we do it the right way. But yeah, hopefully not too bad. I mean, the nice thing about having all this stuff online is hopefully my expectations in terms of like the types of problems that I expect you to know how to do are pretty clear. So make sure to review through all those assignments and stuff. The answer keys are posted at this point. Again, when I say that, everybody's like, great, let me study off the answer key. The real thing that you want to do is prove to yourself that you know how to do it. Sit down, work through it, and then check the answer key. And if you got it, great, right? But if you don't, then you know where you should be working. Okay, I'm gonna stop this.